A lever is a machine consisting of a beam or rigid rod pivoted at a fixed hinge, or fulcrum. A lever is a rigid body capable of rotating on a point on itself. It is one of the 6 simple machines identified by Renaissance scientists. The word entered English about 1300 from Old French, in which the word was l'évər. This sprang from the stem of the verb l'évər, meaning to raise. The verb, in turn, goes back to the Latin ḻɛvər, itself from the adjective ḻiβāis, meaning light. The word's ultimate origin is the Proto-Indo-European stem leg, meaning light, easy, or nimble, among other things. The pi stem also gave rise to the English word light. A lever amplifies an input force to provide a greater output force, which is said to provide leverage. The ratio of the output force to the input force is the mechanical advantage of the lever. Early use. The earliest remaining writings regarding levers date from the 3rd century BC and were provided by Archimedes. "Give me a place to stand, and I shall move the earth with it," is a remark of Archimedes, who formally stated the correct mathematical principle of levers. The distance required to do this might be exemplified in astronomical terms as the approximate distance to the Circinus galaxy, about 9 million light-years. It is assumed that in ancient Egypt, constructors used the lever to move and uplift obelisks weighing more than 100 tons. Force and levers. A lever is a beam connected to ground by a hinge, or pivot, called a fulcrum. The ideal lever does not dissipate or store energy, which means there is no friction in the hinge or bending in the beam. In this case, the power into the lever equals the power out, and the ratio of output to input force is given by the ratio of the distances from the fulcrum to the points of application of these forces. This is known as the law of the lever. The mechanical advantage of a lever can be determined by considering the balance of moments or torque, T, about the fulcrum, where m1 is the input force to the lever and m2 is the output force. The distances A and B are the perpendicular distances between the forces and the fulcrum. The mechanical advantage of the lever is the ratio of output force to input force. This relationship shows that the mechanical advantage can be computed from ratio of the distances from the fulcrum to where the input and output forces are applied to the lever, assuming no losses due to friction, flexibility or wear. Classes of levers. Levers are classified by the relative positions of the fulcrum, effort and resistance. It is common to call the input force the effort and the output force the load or the resistance. This allows the identification of 3 classes of levers by the relative locations of the fulcrum, the resistance and the effort. Class 1. Fulcrum in the middle. The effort is applied on one side of the fulcrum and the resistance on the other side, for example, a seesaw, a crowbar or a pair of scissors. Mechanical advantage may be greater or less than 1. Class 2. Resistance in the middle. The effort is applied on one side of the resistance and the fulcrum is located on the other side, for example, a wheelbarrow, a nutcracker, a bottle opener or the brake pedal of a car. Mechanical advantage is always greater than 1. Class 3. Effort in the middle. The resistance is on one side of the effort and the fulcrum is located on the other side, for example, a pair of tweezers or the human mandible. Mechanical advantage is always less than 1. These cases are described by the mnemonic FRE 123, where the fulcrum is in the middle for the first-class lever, the resistance is in the middle for the second-class lever, and the effort is in the middle for the third-class lever. Law of the lever. The lever is a movable bar that pivots on a fulcrum attached to a fixed point. The lever operates by applying forces at different distances from the fulcrum, or a pivot. Assuming the lever does not dissipate or store energy, the power into the lever must equal the power out of the lever. As the lever rotates around the fulcrum, points farther from this pivot move faster than points closer to the pivot. Therefore, a force applied to a point farther from the pivot must be less than the force located at a point closer in, because power is the product of force and velocity. If A and B are distances from the fulcrum to points A and B, and the force Fa applied to A is the input and the force Fb applied at B is the output, the ratio of the velocities of points A and B is given by B. So we have the ratio of the output force to the input force, or mechanical advantage, is given by this is the law of the lever, which was proven by Archimedes using geometric reasoning. It shows that if the distance A from the fulcrum to where the input force is applied is greater than the distance B from fulcrum to where the output force is applied, then the lever amplifies the input force. On the other hand, if the distance A from the fulcrum to the input force is less than the distance B from the fulcrum to the output force, then the lever reduces the input force. The use of velocity in the static analysis of a lever is an application of the principle of virtual work. Virtual work and the law of the lever. A lever is modeled as a rigid bar connected to a ground frame by a hinge joint called a fulcrum. The lever is operated by applying an input force Fa at a point A located by the coordinate vector r on the bar. The lever then exerts an output force Fb at the point B located by Rb. The rotation of the lever about the fulcrum P is defined by the rotation angle θ in radians. Let the coordinate vector of the point P that defines the fulcrum be Rp, and introduce the lengths which are the distances from the fulcrum to the input point A and to the output point B, respectively. Now introduce the unit vectors each and ebb from the fulcrum to the point A and B. So the velocity of the points A and B are obtained as where each and ebb are unit vectors perpendicular to each and ebb, respectively. The angle θ is the generalized coordinate that defines the configuration of the lever, and the generalized force associated with this coordinate is given by where Fa and Fb are components of the forces that are perpendicular to the radial segments bar and Pb. The principle of virtual work states that at equilibrium the generalized force is zero, that is thus, the ratio of the output force Fb to the input force Fa is obtained as which is the mechanical advantage of the lever. This equation shows that if the distance A from the fulcrum to the point A where the input force is applied is greater than the distance B from fulcrum to the point B where the output force is applied, then the lever amplifies the input force. If the opposite is true, that the distance from the fulcrum to the input point A is less than from the fulcrum to the output point B, then the lever reduces the magnitude of the input force. This is the law of the lever, which was proven by Archimedes using geometric reasoning. Using a rope as a lever. You understand what a lever is. But can you use a rope as a lever? You can if you are using it as shown in the figure. Arrange a strong column at a steep angle. Apply a firm attachment from the rope to the column and the object to be lifted, and apply the force horizontally, and get a great multiplier of force. If one combines the mechanical advantage of pulleys in the horizontal force applier, you could get even greater lifting force. Picture the application in the figure, and in this case, you could get great lift upward, then add planks of wood to support the load at height, reset, and lift again, and add more blocking, and lift, repeat. This technology has been lost in history, as the use of winches with low-friction wheeled pulleys and reduction gearing powered by steam and electricity took over this primitive technology.